Uh, my dear students, welcome to our class. We will continue the D and F block discussion. Today we will discuss isolation of D and F, isolation of lanthanides and the chemical properties of lanthanides. Till 1907, 1907, entire lanthanides were believed to be single elements because of their similarity in properties. That is, cerium, praseodymium, neodymium, europium, lutetium, all 14 elements were believed to be one element because all have similar properties. Okay, but later we could isolate all the lanthanides. Lanthanides are not so trace elements, even though we call them as trace elements, but they are not so trace. They are available in the earth crust in different formats, and certain lanthanides are more abundant than iodine. Among them, promethium Pr is artificial. Among the lanthanides, promethium is artificial. Okay, anyway, we will isolate them by different method. One is from monazite. As for keralites, monazite is very familiar for us. That is what called karimanal. That has been mined from the southern part of the Kerala, Chavara, something like that. Okay, on the coastal area of southern part of the Kerala, particularly Kollam and Alappuzha, where we are mining an ore called monazite. Monazite is very much rich with different types of lanthanides. Monazite is a sand which contains different lanthanide compounds. They have been separated and isolated by this method. Monazite is acidified with concentrated H2SO4. Therefore, we will get a lanthanide salt, where Ln represents cerium, cerium, praseodymium, lutetium, etc. Then we partially neutralize with the base NH4OH, and one particular very costly element, thorium oxide, is obtained, that is precipitated, separated. Then again we will add the sodium sulfate. Lighter lanthanides settled out and separated as sulfate. Therefore, lighter lanthanides are settled and separated as lanthanides. Then again we will go to the salt of lanthanide. Bleaching powder will be added where cerium is deposited as cerium iodate, that could be removed. Then remaining lanthanides are separated by solvent separation method. Okay, this is one method. Now we will go to next method, ion exchange method. Ion exchange. Second is ion exchange method. Ion exchange method. This is the faster and most effective one. Here we will have a long ion exchange column. Ion exchange. This is what is called a ion exchange column. And we will fill here resin. We will fill resins. This is resin containing SO3H, sulfate. To this column we will add lanthanide ion mixture, and it move on through this. Here this resin I have said you SO3H, react with the lanthanide ions, and you will get resin SO3 Ln plus H plus. Okay, you will get like this. Now you collect the resin, then you collect the resin, take the resin back, then add EDTA or citrate. EDTA or citrate. Okay, you will get lanthanide EDTA complex. EDTA complex. Okay. To this lanthanide EDTA complex, you add a magnesium or other metals. Therefore, you will get a free lanthanide plus EDTA and magnesium. This is another method. Okay, ion exchange method. Yes, we have an ion exchange resin. We have ion exchange column, ion exchange resin. Resin contains sulfate groups. In the sulfate group, H plus is exchanged with lanthanide ion, and you will get a lanthanide resin component. You collect it, treat with EDTA, you will get a lanthanide EDTA complex. Then you treat with magnesium or something like that. You will have free lanthanide ions. Okay. This is all about lanthanide. Now let us go to some properties first. Lanthanide shows color. Okay. Lanthanide shows color if it contain unpaired F electrons. Let us say lanthanum 3 plus, cerium 3 plus, Pr 3 plus, Nd 3 plus, Pm 3 plus, Sm 3 plus. Okay. This is F0, F1, F2, F3, F4, F5, F6. Then gadolinium 3 plus, F7. Tb 3 plus, Dy 3 plus, HO 3 plus, Er 3 plus, Tm 3 plus, Yb 3 plus. Lutetium 3 plus. This is F8, F9, F10, F11, F12, F13, F14. Okay. This is colorless. This is also colorless. This is also colorless. This is colorless. First two colorless, last two colorless, the middle one F7 also colorless. Okay, green, lilac, pink, yellow, pale yellow, yellow, pink, pale green, return, pale yellow, yellow, pink, pale green, green. The first two are colorless, last two are colorless, middle F7 also colorless. It is because no unpaired electron, no unpaired electron. Here also no unpaired electron. But in these three cases, they have the unpaired electron still not colored because their transition does not happen in visible region. That's all. Their transition, electronic transition of that three cases, F7, F40, F13, F7 and F1 cases does not happen in visible region. Now, the color is because of FF transition. The color is because of which transition? FF transition. FF transition. Since since F orbitals are n minus 2, that is buried deep, presence of ligand doesn't affect the transition. Hence the band due to FF transition or lanthanides are sharp, very sharp band. We know that if in the spectroscopy you learn that normally an absorption or emission band are like this. This is for DD transition. For an FF transition, the band is so sharp because the width band because of interference of different effects. But FF band is very sharp band. This is because FF transition is very exclusive. Presence of ligands, reactions of ligands does not affect it because F orbitals are n minus 2. What is n? N is the outermost shell. We have an outermost shell there, we have n minus 1 d shell there, and F electrons are not there but in n minus 2. Fine. Therefore, lanthanides compounds are used in spectroscopic analysis, that is calibration of instrument. What is a calibration? Calibration means we are checking if our instrument is proper or not. That can be done using lanthanide compounds, because when you use the lanthanide compound you will get very sharp line. If you get the sharp line means your instrument is okay, because you cannot use d orbital d compounds, because d compound always gives, actually naturally gives width, band, wide band. Therefore we cannot recognize that if the wide band because of the compound or because of the error of the instrument. Okay, therefore calibration of instrument could be done by lanthanide compound. Another one, FF orbital is, FF transition is lab part forbidden. When photochemistry was discussed, I have a detailed video in photochemistry about lab allowed and forbidden transition. You just watch it. Now let us go to the magnetic property. Magnetic property. Lanthanides are paramagnetic. Lanthanides are paramagnetic if they have unpaired electron. Now again, Ln3 plus, cerium 3 plus, this is F0, this is F1, 3 plus, Nd3 plus, Pm3 plus, Sm3 plus, Gd3 plus, Dy3 plus, Tb3 plus, HO3 plus, ER3 plus, Tm3 plus, YB3 plus, Lu3 plus. F1, F2, F3, F4, F5, F6, F7, F8, F9, F10, F11, F something. Okay, here is something missing. EU. Here, this is, sorry. F6, 7, 8, 9, 10, 11, 12, 13, 14. Therefore, this is diamagnetic. This is also diamagnetic. Now, I tell you one more point. Cerium plus 4 also diamagnetic. Because cerium plus 3, 1 F electrons. Cerium plus 4 has no F electrons. Therefore, except Ln, lanthanide, cerium plus 4 and lutetium 3 plus, all others are paramagnetic. These two are diamagnetic. Okay. Are you okay? La3 plus and lutetium 3 plus are diamagnetic because they have no unpaired electron. Rest all are paramagnetic. Yes. Now, the magnetic moment of lanthanide is calculated by the equation mu is equal to square root of n into n plus 2 plus L into L plus 1. What is this? Confusing. In the case of a D block element, D block, this is F block, magnetic moment is n into n plus 2. What is n? Number of unpaired electrons. L is orbital contribution. We know that an electron is spinning as well as, suppose this is an orbit or orbital. An electron is spinning like this. Because of the spinning, we will have a magnetic moment. Because electron is a charged particle. When electrons spin like this, okay. When electrons spin like this, it will have a magnetic moment that is represented by n. Therefore, n is also called a magnetic moment due to spinning of electron. L is magnetic moment due to orbital motion. In addition to the spinning, electron is revolving around the nucleus. Okay, it revolves. But that orbital motion is not accounted in D transition metal, D block metals when we count their magnetic moment. When transition metal magnetic moment is considered, orbital motion is not accounted, but that has been accounted in F block elements, in lanthanides, as well as in actinides also. Therefore, lanthanides magnetic moment calculation is quite complex and little confusing. But you understand this point, orbital motion also accounted in their magnetic moment. Therefore, this is the equation for magnetic moment calculation of lanthanides. Also, two important properties of lanthanides. Now, let us go to the chemical properties. Ln. Ln means lanthanum to lutetium. Okay. When it reacts with any acid, it produces hydrogen gas. When it reacts with oxygen, they will form Ln2O3, oxides. When it reacts with sulfur, Ln2S3, that is sulfides. When it reacts with nitrogen, you will have a nitrite. When it reacts with the halogen, you will have LNX3, halides. When it reacts with the carbon, you will have LnC2, Ln2C3, like that. Different compounds. Okay. Now, very important point, chloride, nitrate, sulfates. Chloride, nitrite, chlorides, nitrates, sulfides are soluble. They are soluble. Lanthanides compounds are soluble. Okay? Yes. This is all about the chemical properties. Now, next topic is lanthanide contraction. We will discuss in another video. Thank you for watching.